We spent some time on Monday briefly introducing Newton's law of universal gravitation. We said that every two objects, whether they be the apple and the earth, or whether they be the earth and the sun, or whether they be two apples, exert a force of gravity on each other. The bigger the masses, the bigger the force of gravity that they exert on each other. Now, that force of gravity we learned yesterday can be quantified by an equation, the Newton's law of universal gravitation equation. It says the force of gravity, the force of gravitational attraction between those two objects, whether they be the apple and the apple or the earth and the sun, is related to the product of the masses. So in other words, you multiply the two masses together in whatever order you want. The earth times the apple, or sorry, the earth times the sun, or the sun times the earth. The product of the masses, but it's inversely related to the distance between the centers of the two objects. So from the center of one apple to the center of the next, to the center of the earth to the center of the sun. The distance between the objects squared. Now, it's not equal to that equation that you see up there, but it's related to those variables that you see up there. It's equal to a number, a constant, times those variables. A constant we're going to call the gravitational constant, big G. Its value is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Don't get that mixed up with little g. Two completely different values. Here, little g is 9.81, about, depending upon where you are on Earth. Big G is 6.67 times 10 to the minus 11. So there's a pretty big difference in the values there. All right? We calculated, I believe, on Monday, the gravitational force of attraction between two people. We found that gravitational force of attraction, I think, to be in the range of 10 to the minus 7 newtons. It's a small force because the mass of two people are really, really small. But if you calculate the force of gravity between, all of a sudden, the Earth and the apple, or the Earth and you, or the Earth and the sun, all of a sudden that number becomes a lot bigger because of the mass of the Earth. All right. We had, yesterday, some problems that we were working on with gravitational force and Newton's law of universal gravitation. The first two problems that we had were on page 207. Were there any issues with questions 1 and 2 on 207? No? They're good? For the people that were here, that is. They're good? Okay, I want to do number 1 anyways. Just as a bit of a review, just to make sure for the people that were here that this is okay, and for the people that weren't here, just so that we can at least show you one good example of this law of gravitation stuff. This one says two people, A and B, are sitting on a bench 0.6 meters apart. Person A is 55, person B is 80. What's the force of gravity between the two of them? Now, this is much like the question we did the other day, but 2 days removed. Force of gravity exerted by B on A. We're going to say that the magnitude of the force of gravity is G m1 m2 over r squared. Does it matter whether I put that division sign there? What do you call that, math people? Division sign there. Does it matter whether that division sign is just under m1 m2, or could I stretch it over underneath the G? Does it really matter? No, it doesn't matter. G times m1 m2 over r squared, or G m1 m2 all over r squared, it gives you exactly the same value. Okay, so let's do that. 6.67 times 10 to the minus 11 times mass 1. Which one do I use as mass 1, 55 or 80? I got a question for you. Okay, I got a question for you. Sam, what's 2 times 3? Sam, you know what I asked Sam? Because I knew Sam would know. Sam's a smart guy. I knew he'd know the answer to that question, 2 times 3. Excellent, Sam, you nailed that. 2 times 3 is 6. Now I'm going to give you a harder one. Okay, Victoria, what's 3 times 2? Okay, see? Ask the two smart people, right? Because you know they're going to get 3 times 2 and 2 times 3. Good. The point is 2 times 3 is the same as 3 times 2, right? M1 times M2 is the same as M2 times M1. 55 times 80 is the same as 80 times 55. Does it matter which one I make first? No. So let's go. Now let's put them in the order that they're listed. 55 times 80. But if you put them the other way around, it's going to give you the same answer, right? Divide that by the distance squared, 0.60 And we got to square that. Let's pull out the calculator to do this as a group here. Let's say 6.67 times 10 to the minus 11 times, oops, that's not right, EE, which is 10 to the minus 11, times 55 times 80, or times 80 times 55, divided by 0.6 squared. 0.6 squared, there we go. Works out to be 8.15, or 8.2 times 10 to the minus 7 newtons. Hey, now I got a question for you. Okay, the question said, what's the force exerted by B on A? This is the value we got. How do we know this is the force of B on A, not the force of A on B? Did we just get lucky and solve for the right one? Or did we know what we were doing here yet, Nathan? It's the same force. And how do you know that? Let's go back to last unit. I told you guys when I was telling you about your test next Wednesday that there's a lot less in this unit, right? But it still relates back to the last unit somewhat. Newton's third law, if object A applies a force on B, object B applies an equal and opposite force on A. So what I'm saying is that basically if the 55 kilogram guy applies a force on the 80, then the 80 kilogram guy applies an equal and opposite force back on the 55. So here's the force of B on A. That's also the force of A on B. The magnitude, at least. The magnitude. The direction, opposite direction. Okay, same magnitude. Let's put that in different terms here. That apple falls from a tree, hits Newton in the head. The Earth applies a gravitational force on the apple. Does that mean the apple applies an equal and opposite force back on the Earth? Yes. Yes. So why is it if the apple falls toward the Earth when it's the same force of gravity on the apple as it is on the Earth? Why does the apple fall towards the Earth versus the Earth rising up towards the apple? Same force. Julia? The Earth is bigger. And this comes back to Newton's second law. If you got the same force, but a much bigger mass, then the acceleration is much smaller. So does the Earth rise toward the apple? Yes. But because its mass is so big, the acceleration is so ridiculously small that you never, ever notice it, right? Make sense? Okay. We also gave you a couple problems from yesterday on page 209, and these relate to problems involving gravity, but gravity between three objects. So I think in both of these cases it was the Earth, the Moon, and the Sun. It could be the force of gravity between person A, person B, and person C. Okay, three people, either in a row or, as I left you with question 2 yesterday, three people or three objects like this. Okay, let's do question number 1 here, whether you think you need it gone over or not. We have the Earth, the Moon, and the Sun here. And we got the masses of these objects. They're on our data sheet. Okay, the Sun, I think, is 1.99 times 10 to the 30, and the Earth is 5.97 times 10 to the 28. And I can't remember what the Earth, 10 to the 24. I can't remember what the Moon's mass is. Something times 10 to the 22, I think. Okay. They're on our data sheet. We don't need to memorize those numbers. We know that they have a lot of mass. We know there's a force of gravity between all three of these things. But we want to find the net gravitational force. Net means, what's another word for net? A 5-letter T word. Let's go, Nathan, number 2. Total. It's the total force. So if you're looking at the Earth, there is a force of gravity caused by the Moon on the Earth. The Moon pulls the Earth this way. We're going to call that FME, the force of the Moon on the Earth. It's toward the Moon. Now, the Moon is pulled toward the Earth as well, but we don't really care what happens to the Moon because that's not the problem. The problem is what happens to the Earth here. There's also a force of the Sun on the Earth. The Sun pulls the Earth to the right as well. We'll call that FSE, the force of the sun on the Earth. Two forces to the right. Is this not a problem that we've done 1,000 times before, deep down? We've got two forces acting on an object. What do we do when we have two forces acting on an object? What did we do when we had vertical circular motion? What did we do when we had an elevator problem? What did we do when we had an inclined plane problem? What did we do when we had a pulley problem? What's my next step? F net is equal to the sum of the forces. Now, we don't know what the value of FSE or FME is, so we got to find it. But we know how to find it. That's what we did in the last set of questions. This is what we did last unit and what we did last week. F net is equal to the sum of the forces combined with what we did yesterday, calculating each of these forces. So let's get FSE, the force of the sun on the Earth. It's equal to G m1 m2 over r squared. It's 6.67 times 10 to the minus 11 times the mass of the Earth, which, check your data sheets, I believe it's 5.97 times 10 to the 24. And the mass of the sun, I think it's 1.99 times 10 to the 30. Again, check that for me. The distance that separates the Earth and the sun, 1.50 times 10 to the 11. And we got to square that. Nathan, 3.52 times 10 to the 22 newtons. Anybody agree with that? Yes? Thank you, Sam. All right, good. Let's get the force of the moon on the Earth now. It's equal to 6.67 times 10 to the minus 11 times the mass of the Earth, which is, once again, 5.97. That I said 5.79 down here. It should be 5.97 times 10 to the 24 times the mass of the moon, which is 7.36 times 10 to the 22 newtons. The distance, hey, look, the mass is smaller, which you think would give you a smaller force of gravity, right? But the distance is also smaller. We got 3.84 times 10 to the 8 squared. Looks kind of ugly there. What do you get there? .0 times 10 to the 20. So the force is 100 times smaller, right? Why is it 100 times smaller? Because the mass of the moon is a lot smaller than the mass of the Earth. Now, the force of gravity isn't as small as you might expect when you compare these two masses, 10 to the 22 kilograms, 10 to the 30 kilograms. But remember, it's also a lot closer. So the decreased mass makes gravity bigger. The decreased distance makes gravity smaller. So they almost counter each other. Okay, now we got to add these things together. So it's going to be the force of the sun on the Earth. It's going to be 3.52 times 10 to the 22 newtons, plus the force of the moon on the Earth, 2.0 times 10 to the 20. Do we have to worry about a negative sign here? Either of them negative? No. No. How do you know? Yep. No, careful there. It's not the absolute value here anymore. When we solve for these forces, we solve for the magnitude of the absolute values. But now we're plugging them in as being in a particular direction. F net is equal to the sum of the forces. Not the sum of the magnitudes, but the sum of the forces including direction. They're both in the same direction. They're both to the right, both positive. If one was to the left, we wouldn't have got a negative value for it here, but we'd plug it into our red expression here as a negative value. Right, Sam? Good. Calculate that value, add these up, and I assume we get 3.54 times 10 to the 22 now. And of course, it means toward the center, toward the sun, right? Toward the sun, because both of them are toward the sun. Good. Now, the last thing that I left you with yesterday was the bottom problem. And I hadn't actually shown you how yesterday to solve this bottom problem. Does anybody feel confident that they got this problem? Somebody who wasn't here? Yes? What'd you do? So you actually saw the answer at the bottom of the page? So you know you got the answer right. Okay, good. Good, Tyler. So what'd you do then? Okay, so you do your free body diagram. Okay, we got a force to the right. That's the force of the sun on the earth. We have a force upward. That's the force of the moon on the earth. Now, the values of those two forces are the same as they were in the last question, right? Not a whole lot of work to do for this problem. We've got this value. We've got this value. And then Tyler recognized, wait, this is the same problem as we saw in our last unit and even in our first unit when we were adding displacement vectors together. You want to add two vectors together that aren't on the same axis? We got to add the forces, but we're not adding them together this way. We're adding them together this way. Here's the force of the sun on the earth to the right. Here's the force of the moon on the earth up this way. The net force goes from start to finish, the sum of the forces, and we got to find the net force by, Tyler again, the Pythagorean theorem. Yeah, a squared plus b squared equals c squared. And we got to find that angle by the inverse tan function. Okay, I purposely, consciously didn't show you how to do, for those of you who are here, didn't show you how to do question number 2 yesterday. I wanted to see if you could figure it out. Tyler figured it out. Good for you. And I'm sure that probably a few other people figured it out as well. I love it when I can do that. And this is the time of year that I can start doing that. I can give you a question like this that you've never seen before, and you can use your brain and figure it out. This is we're going in questions like this from a problem where we're remembering something to a problem where we're thinking about something and able to extend it to something new. And that's exactly where we want to get. Okay, so for those of you who got it, good job. Okay, if you didn't, that's okay. Don't panic about that. But just kind of think of it bigger picture like that. All right, let's move forward here. There's been a number of things in the last several days where we've looked deeper. So we started off with Kepler's laws, Kepler's 3 laws. It describes the motion of the planets, not why the planets do what they do, but just how they do what they do. And then we said, well, why? And then so Newton comes along and answers that question. It's because of gravity. There's a force of gravity between any two objects with mass. One day we talked about why there's a force of gravity between any two objects with mass, right? Einstein, the curvature of space-time with mass, and so on and so on and so on. We said that there is a reason why gravity acts between two objects. Newton didn't know what that reason was, but Newton explained very, very well what the magnitude of that force of gravity was. That equation, F is equal to G m1 m2 over r squared, works to this day, a few hundred years later, perfectly. It just doesn't tell us why, but it works perfectly. Well, if we dig a little deeper here, there's one question that we haven't answered yet. We may have not even asked it in our minds. I told you the force of gravity between any two objects was, as Newton told us, G m1 m2 over r squared. And I told you this value was 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Where did that come from? Like, did you guys just trust me that this number multiplied by m1 m2 over r squared gives you the correct force of gravity? Yeah, probably you did. And you know what? If I was in your spot, I probably would have done the same thing. I probably would have trusted you as well. But did it occur to anyone that this seems like a pretty random number? Like 9.81 seems like a random number. 6.67 times 10 to the minus 11 sounds like, I don't know if you can get even more random than random, but even more random than random. Extremely random, yes. This did come from something. It came from an experiment performed by a guy named Cavendish. Newton knew what the relationship was between mass and distance. Okay, and that was a huge step forward, but he didn't know what that value of g was that should be in front of all that. So we rely on Cavendish to figure out what that value of g was. This represents the ceiling or the top of a box or something that can hold a string or a piece of wire hanging from it. On the end of that string is going to be a thin, fairly light rod. On the end of each of those, or on each end of that rod, is going to be a mass. We're going to call this one M1. We're going to call this one M, trick question, M1. It's the same value of mass. We don't want this thing to tip over. Okay, it's a rod hanging from a string. If it's different masses, what happens? It tips over. Okay, we want it to be balanced. My fist is going to represent M2. So I'm going to bring M2, which is my fist, toward M1. It doesn't matter which M1. Okay, let's make it toward the left one. You can see the shadow on the board there of my fist. As M2 gets closer to M1, what's going to happen? There will be a very, very, very small force of attraction between M1 and M2. This M1 is going to start turning. It's going to start moving towards M2. So here's M2 going towards M1, and M1 starts coming towards it. A very small amount, but still an amount. So what Cavendish does is this. He measures the value of M1. That's easy, he says. Hey, M1 is use a scale. The bigger the mass, the better, because the more of an effect you have. Use a scale, measure the value of M1. M2, my fist, as I bring it towards it, that's easy to find the mass of as well. Get the value of M2. R, well, that's easy enough. Use a ruler to measure the distance that separates M1 and M2. If Cavendish wants to find the value of G, the gravitational constant here, remember, he doesn't know this yet. Okay, right now, this is a big question mark. What's the value of big G? If he wants to find the value of G, he needs M1, M2, R, and he also needs F, the other variable. That's the one that's trickier to find. How do you measure the value of F? You can't just pull out those electronic sensors, force sensors that we used in our friction lab. You can't just pull out a spring scale or a bathroom scale to measure the force that exists between these two. Let's take you to your childhood to help you to understand this. Everybody's done this. You go to the playground, you go on the swing set, you start swinging, and then you start getting a little bit bored because you got as high as you can get, and then you're hanging straight down and you twist it. You twist the swing around as many times as you can, and then you let it go so that you start spinning, right? You guys have all done that, right? Everybody that's done that knows that the more you twist it, the harder it is to twist, right? In other words, the more you twist it, the more force is required to twist it. You could, if you wanted to, you wouldn't do this when you're 5 years old. You probably wouldn't even do this when you're 17 years old or 16 years old, however old each of you are. But you could, if you wanted to, do a little experiment to test how much force was required to twist it a quarter of a turn, or a half a turn, or 3/4 of a turn, and so on. You could determine how much force was required to twist it a certain amount, and then from that, you could have a little chart that says, hey, next time I twist this around, oh, I twisted it at 1 1/4 turns. That must be that much force. That's what Cavendish would have done here. He would know how much force was required to twist this string 3 degrees, 8 degrees, 12 degrees, whatever the case may be. So he's able to measure the force not from a scale between the two masses, but he's able to measure the force from this scale by observing how much the string twists. You guys know what the word torsion means? Twisting. It's the twisting balance experiment. We're able to determine the force by observing how much the string twists. So now we got M1, now we've got M2, now we've got R, now we've got F. And although I'm simplifying this a little bit, basically what it comes down to is rearrange the equation, solve for G. And when you do that, when Cavendish did this, it works out to be 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Does that make sense? Got some questions for you to work on page 215. For homework, I'd like you to do the following questions. Number 1 and 2, and 4 to 6. So everything up to number 6 except for question number 3. You know what, I'm going to give you, I'll give you about 6 or 7 minutes to work on these questions now, just to get a start so that you can ask me questions right now while I'm here if you have them. Finish the rest of them up for homework tonight, and we'll take a look at them tomorrow.